Every rule of air combat at the start of the Second World War pointed in the same direction. If you removed armor, you exposed the crew. If you removed defensive guns, you invited interception. And if you sent an aircraft deep into enemy airspace alone, without protection, you accepted that it probably would not come back. In 1940, that logic was not controversial. It was accepted doctrine. And yet, one aircraft entered service that deliberately rejected almost every one of those assumptions. It carried no defensive turrets in its early roles. It relied on speed instead of protection. It was built around a structure that many people still misunderstand today. And it was sent into missions where failure meant instant loss, not damage, not retreat. The de Havilland Mosquito did not survive because it broke the laws of air combat. It survived because it operated inside a very narrow set of conditions where those laws no longer applied in the same way. When everything aligned, the aircraft worked. When one variable failed, it did not. This is not a story about a miracle aircraft. It is about why the Mosquito worked when logic said it should not, and why that same logic would have destroyed almost any other airplane built the same way. If this kind of careful military history matters to you, consider subscribing to the channel. And let us know in the comments where you are watching from, your city and your country. Now, let's start with the logic that said this aircraft should never have worked at all. At the beginning of the Second World War, bomber survival was built around one central assumption. Aircraft survived by absorbing punishment and returning fire. This assumption shaped almost every bomber design of the late 1930s. Multiple crew positions, defensive gun turrets covering every approach angle, thick structural members designed to tolerate damage, and formations that allowed overlapping fields of fire. These aircraft were heavy, complex, and slow, but they were designed to fight their way through defended airspace. British bombers like the Wellington and the Sterling followed this logic. So did American designs that would appear later, such as the B-17. The idea was not speed, it was endurance. The problem with this approach was physics. Every gun added weight. Every turret increased drag. Every additional crew member required space, oxygen, and protection. The aircraft became harder to accelerate, slower to climb, and easier to intercept. By 1941, the cost of this logic was becoming impossible to ignore. Loss rates were rising. Crews were being lost faster than they could be replaced, and defensive fire, even when concentrated, did not guarantee survival against modern fighters. The alternative solution seemed irrational. What if an aircraft did not try to survive interception at all? What if it was designed to avoid it completely? This was not a new idea, but it was one that most air forces had dismissed. Speed alone was considered unreliable protection. If a fighter caught you, you had nothing to fight back with. And if you miscalculated altitude, timing, or route, the aircraft would be defenseless. That risk was real, and the designers of the Mosquito understood it. The Mosquito was not built on the belief that armor and guns were useless. It was built on the belief that there were missions where armor and guns imposed a greater penalty than the protection they provided. Reconnaissance flights, precision strikes, intruder operations, missions where the goal was not to fight the enemy's fighters, but to avoid them entirely. This distinction matters. The Mosquito was never intended to replace every bomber. It was intended to operate in roles where speed, altitude management, and careful planning could substitute for brute force. That decision reshaped everything else about the aircraft. Crew size was reduced. The fuselage was kept aerodynamically clean. Defensive armament was removed in early variants, not as a gamble, but as a calculated trade-off. Every kilogram saved translated into performance. But this approach created a narrow margin for error. The Mosquito could not afford mistakes. It could not loiter. It could not improvise when intercepted. It depended on precise navigation, disciplined flying, and strict mission planning. In other words, it worked only when the assumptions behind it were respected. This is where much of the mythology begins. Speed did not make the Mosquito invulnerable. It made it conditionally survivable. Understanding that difference is essential because everything that follows, from its structure to its operational record, depends on that narrow window where logic appeared to fail, but in reality had simply been redefined. One of the fastest ways to lose credibility when talking about the Mosquito is to blur the question of authorship. This aircraft was not a Canadian design, and it does not need to be for Canada's role in its story to matter. The Mosquito originated in Britain, inside the de Havilland Company, under the leadership of Sir Geoffrey de Havilland. That point is not controversial, and it should never be softened for narrative convenience. What is often misunderstood is how much of the aircraft's success depended not on a single designer, but on a collective engineering culture that accepted risk where other institutions refused it. In the late 1930s, the British Air Ministry was conservative by necessity. It had been burned before by ambitious projects that promised performance and delivered delays. Its procurement philosophy favored proven concepts, incremental improvements, and predictable production. The Mosquito proposal challenged all three. It was not simply an aircraft made from unconventional materials. It was an aircraft that rejected prevailing assumptions about survivability, crew protection, and armament. From an institutional point of view, that made it dangerous, not innovative. Geoffrey de Havilland understood this resistance. He did not argue that armor and guns were obsolete. He argued that they were inappropriate for certain missions, and that the penalty they imposed could outweigh their benefits. That distinction mattered, but it did not remove the risk. The Mosquito was approved cautiously, in stages, and under constant scrutiny. Early prototypes were watched closely. Performance claims were tested, not accepted at face value. The aircraft was allowed to proceed not because everyone believed in it, but because its potential advantages were measurable. This is an important correction to the popular story. The Mosquito was not born out of desperation or improvisation. It was the result of calculated decisions made by engineers who understood exactly what they were giving up in exchange for performance. Those decisions extended beyond aerodynamics. The aircraft structure required precise manufacturing, careful bonding, and quality control that could not tolerate shortcuts. This was not furniture work in the casual sense. It was industrial production using woodworking techniques refined to aerospace standards. That distinction becomes critical when the story moves beyond Britain. As the war expanded, production demands exceeded what British factories alone could supply. Aircraft manufacturing had to be dispersed, both to increase output and to reduce vulnerability to bombing. This is where Canada enters the story in a way that is often misunderstood. Canada did not design the Mosquito, but Canada became essential to its production and operational success. De Havilland Canada, based at Downsview in Ontario, took on the task of manufacturing the aircraft under license. This was not a simple matter of copying drawings. Canadian factories had to adapt processes to local materials, local labor, and local supply chains, while maintaining strict tolerances. Wood quality varied. Adhesives had to be sourced reliably. Environmental conditions differed from those in Britain. The Mosquito's design allowed this flexibility, but it did not forgive poor execution. That meant Canadian-built aircraft were not good enough versions. They had to meet the same performance and structural standards as those built in Britain, or they were unacceptable. This requirement shaped Canadian industrial practice during the war. Skilled labor had to be trained quickly. Quality control systems had to be enforced without compromise. And production had to scale without degrading the aircraft's defining characteristics. In operational terms, Canadian involvement extended beyond manufacturing. Royal Canadian Air Force squadrons flew the Mosquito in demanding roles: night fighter operations, intruder missions, high-risk sorties where timing, navigation, and discipline mattered as much as raw performance. These were not forgiving missions. The Mosquito did not offer its crews the option to fight their way out of mistakes. In Canadian hands, as in British service, success depended on respecting the aircraft's limits. This is why authorship matters. The Mosquito was not a national symbol in the way some weapon systems become. It was a shared effort built on a British design, refined through multinational production, and validated through operational use by crews who understood exactly what they were flying. Treating it as a purely Canadian invention invites correction. Treating it as a purely British achievement ignores the reality of wartime production and service. The Mosquito worked because engineers, manufacturers, and air crews across the Commonwealth understood the same principle. Innovation does not survive on belief, it survives on execution. and the Mosquito's execution across design, production, and operations left no room for myth. Few aspects of the Mosquito generate more misunderstanding than its structure. It is often described casually and incorrectly as a wooden airplane, as if that single word explains both its success and its limitations. It does not. At the time the Mosquito was designed, engineers did not speak in terms of composite materials the way we do today. That language belongs to a later era, shaped by fiberglass, carbon fiber, and synthetic resins. But the principle behind the Mosquito's structure is one that modern engineers would immediately recognize. The aircraft used what was known at the time as sandwich construction. The fuselage was built around molded shells formed from layers of laminated plywood with a lightweight core material between them. Each layer served a specific purpose. The outer skins handled tensile and compressive loads. The core increased stiffness without adding significant weight. The result was a structure that was light, rigid, and aerodynamically smooth. This was not carpentry in the civilian sense. It was aerospace manufacturing using wood as a structural medium. The materials were selected carefully. High-quality plywood was used for the skins. Lightweight core material, often balsa, provided thickness and rigidity. And most importantly, the layers were bonded together using structural adhesives under controlled conditions. This bonding mattered. Unlike riveted metal structures where loads are concentrated around fasteners, the Mosquito's bonded shells distributed stress across large surface areas. That reduced stress concentrations and allowed the structure to remain stiff at lower weight. The manufacturing process reflected this precision. Sections of the fuselage were formed in large molds, ensuring consistent shape and alignment. The adhesive was cured under pressure, using clamps and controlled heat where required. Once bonded, the shells became a single structural unit, not a collection of parts. This approach produced a surface that was exceptionally smooth by the standards of the time. That smoothness reduced aerodynamic drag, which directly translated into speed. It is important to be precise here. The Mosquito was not faster because it was made from wood. It was faster because its structure allowed engineers to reduce weight and drag simultaneously, without sacrificing the stiffness required for high-speed flight. Wood was the means, not the explanation. There were also practical advantages. Woodworking skills were widely available. Production could be distributed across facilities that did not compete directly with aluminum-intensive industries. And strategic materials like aluminum could be conserved for other aircraft where they were essential. But these advantages came with conditions. The quality of the structure depended entirely on workmanship. Poor bonding, inconsistent materials, or rushed curing could compromise the entire airframe. There was no tolerance for shortcuts. This is why the Mosquito structure cannot be reduced to a joke about furniture or glue. The aircraft demanded industrial discipline. Factories had to maintain tight quality control. Workers had to be trained to aerospace standards, not civilian ones, and inspection procedures had to catch defects before they reached the flight line. Modern engineers might describe the Mosquito as an early example of composite thinking, not because the term existed at the time, but because the design philosophy was the same. Different materials were combined so that each handled a specific type of load. The structure worked as a system, not as a collection of independent components. That system was effective, but it was not forgiving. Damage that might be tolerated in a metal airframe could be more difficult to assess in a bonded structure. Fire posed a serious threat, as it did to all aircraft carrying fuel, but the consequences of structural damage could escalate quickly if not addressed. Again, this reinforces the central theme. The Mosquito's design worked within a narrow envelope of assumptions: high-quality manufacturing, careful maintenance, and disciplined operational use. When those conditions were met, the structure performed exceptionally well. When they were not, the aircraft offered little margin for error. Calling the Mosquito made of wood simplifies the story to the point of distortion. Understanding how it was built explains why it worked, and why the same approach would not have succeeded without the industrial control that supported it. Speed was never meant to make the Mosquito invulnerable. It was meant to make interception unlikely. That distinction matters. because much of the mythology surrounding the aircraft collapses when speed is treated as a magic shield rather than a conditional advantage. The Mosquito's performance advantage came from a combination of factors: low aerodynamic drag, high power-to-weight ratio, and an operational philosophy that treated energy management as survival, not convenience. In practical terms, this meant flying profiles that maximized speed and minimized exposure. Routes were planned carefully. Timing mattered. Altitude was chosen based on mission requirements, not habit. This is where many simplified accounts go wrong. The Mosquito did not always fly at extreme altitude. Some missions were conducted high, others at medium altitude, and some deliberately low depending on the role. There was no single Mosquito altitude. What mattered was energy. Energy in air combat is a combination of speed and altitude. Altitude can be traded for speed. Speed can be traded for maneuverability or escape. The Mosquito was designed to operate with enough excess energy that if intercepted, it could disengage before a fighter could bring weapons to bear. This worked under specific conditions: against fighters already at altitude, against interceptors that required time to climb, against defensive systems that relied on early detection and interception planning. It did not work universally. If the Mosquito was caught at low energy, if it was surprised at low altitude without room to accelerate, or if interception occurred at a point where escape routes were limited, the aircraft had no defensive fallback. There were no rear gunners to drive off an attacker, no armor to absorb repeated hits. Once intercepted under unfavorable conditions, survival depended entirely on pilot skill and luck. Altitude introduced another constraint. Above a certain height, human physiology becomes a limiting factor. By the early 1940s, this was well understood. Oxygen systems were standard equipment for high-altitude flight long before the Mosquito entered service. They were not experimental, and they were not optional. When Mosquito crews operated at higher altitudes, they did so using oxygen masks connected to onboard systems. This was routine procedure across all major air forces. There was nothing romantic about it. Flying on oxygen was uncomfortable. Masks restricted movement, fatigue increased, cold intensified, and the cockpit was not pressurized. This placed strict limits on how long crews could remain at altitude, how complex their tasks could be, and how quickly errors accumulated. Again, the aircraft worked because its missions were planned around these realities, not in spite of them. Speed alone was not enough. Speed had to be preserved. This influenced everything from engine management to navigation. Abrupt maneuvering increased drag and bled energy. Poor navigation extended exposure time. Delays increased the chance of interception. Mosquito crews were trained to avoid combat entirely. If a mission turned into a chase, something had already gone wrong. This is an uncomfortable truth that is often omitted. The Mosquito was not a fighter in its early unarmed roles. It was an aircraft that survived by refusing combat, not by winning it. Later variants would add armament, radar, and new mission profiles. But the original logic remained. Protection was achieved not through resistance, but through avoidance. This approach demanded discipline. Crews could not improvise freely. They could not linger over targets. They could not react emotionally to threats. The aircraft rewarded precision and punished hesitation. When flown exactly as intended, the Mosquito could pass through defended airspace with remarkable effectiveness. When flown outside its intended envelope, it offered no mercy. This is the core reason why the Mosquito worked, when logic said it should not because it ignored the rules of air combat, but because it operated within a carefully defined space where those rules bent, but never disappeared. One of the most common ways the Mosquito is misrepresented is by treating it as a single aircraft with a single identity. It was not. The Mosquito was a family of aircraft, adapted continuously to different missions, threats, and stages of the war. Understanding why it worked requires understanding which Mosquito was doing what and when. Early Mosquito variants were designed around speed and reach. Photo reconnaissance aircraft, for example, often carried little to no armament. Their survival depended entirely on performance, altitude management, and route planning. In this role, every kilogram mattered. Cameras replaced guns. Fuel replaced armor. The aircraft was stripped to its essentials because its purpose was not to fight, but to see and return. Bomber variants followed a similar philosophy at first. The original bomber Mosquitoes carried modest bomb loads compared to heavy bombers, but they delivered them with precision and speed. They were used against specific targets where timing and accuracy mattered more than mass. These aircraft did not loiter. They did not circle targets. They struck and left. As the war progressed, the aircraft's versatility became impossible to ignore. Fighter-bomber variants were introduced, carrying forward-firing cannon and machine guns in the nose. These versions could engage ground targets directly, combining speed with concentrated firepower. This is where many simplified narratives collapse. The Mosquito was not unarmed in general. It was unarmed in specific variants for specific missions at specific points in the war. Later versions carried substantial armament: 420mm cannon in the nose, additional machine guns depending on the mark, external stores, rockets, and heavier bomb loads as structural limits were expanded. Night fighter variants added another layer of complexity. These aircraft carried radar, additional crew, and different mission profiles. They operated in darkness, intercepting enemy bombers and intruders. Speed remained important, but endurance, situational awareness, and coordination became equally critical. Each of these roles imposed different compromises. Adding radar increased weight and drag. Adding armament reduced range. Adding crew increased workload and coordination requirements. The Mosquito could absorb these changes only because its basic design offered performance margins to trade, but those margins were not unlimited. As variants accumulated weight and complexity, the aircraft's original advantage narrowed. Later Mosquitoes were still effective, but they were no longer operating on the razor-thin assumptions of the earliest versions. This is where chronology becomes essential. Statements that are true for a reconnaissance Mosquito in 1942 may be false for a fighter bomber in 1944. Performance figures change, operational risk changes, survivability changes. Ignoring this leads to exactly the kind of errors that provoke critical audiences. The Mosquito was not faster than every fighter in every situation. It was faster than many interceptors under certain conditions, at certain times, in certain configurations. It did not outfly the enemy as a universal rule. It exploited gaps in detection, response time, and climb performance. This is also where comparisons with German fighters are often mishandled. Early in the war, interception depended heavily on ground control, radar coverage, and climb rate. A fast aircraft operating at the right altitude could pass through defended zones before fighters could be vectored into position. Later in the war, interception improved. Fighter performance increased. The margins narrowed. The Mosquito remained effective not because it froze in time, but because it adapted. Understanding the aircraft means tracking that evolution, not collapsing it into a single legend. The Mosquito worked because it was flexible, but only within limits. Each new role demanded careful reassessment of risk. That reassessment is missing from most popular accounts, and without it, the Mosquito becomes a myth rather than what it actually was. A highly specialized aircraft family, successful because it was used intelligently, not because it was universally superior. Canada's place in the Mosquito story does not begin with design, it begins with execution. When Mosquito production expanded beyond Britain, Canada became a critical industrial partner. De Havilland Canada, operating from facilities in Ontario, produced aircraft under license at a time when speed of delivery mattered as much as innovation. This was not a symbolic contribution. Building the Mosquito demanded precision. The aircraft's bonded structure required consistent materials, controlled processes, and strict inspection standards. Small deviations in workmanship could compromise the entire airframe. Canadian factories had to meet the same structural and performance requirements as British plants. There was no export tolerance. An aircraft that failed inspection did not fly. This mattered operationally. The Mosquito did not forgive structural weakness. It operated at high speed, often near the limits of its design envelope. Any flaw introduced during manufacturing would be exposed quickly in service. Canada's success in producing the Mosquito was therefore not a matter of volume alone. It was a matter of maintaining quality under pressure. Beyond production, Canadian aircrews flew the Mosquito in demanding roles. Royal Canadian Air Force squadrons operated the aircraft in night fighter and intruder missions, where timing, navigation, and crew coordination were critical. These were not forgiving assignments. Intruder missions required aircraft to cross enemy lines at night, often at low or medium altitude, striking airfields, rail yards, and transport nodes. Surprise mattered more than firepower. Navigation errors could be fatal. Night fighter operations added another layer of complexity. Radar equipment increased workload. Crew coordination became essential. Speed remained important, but situational awareness determined survival. In these roles, the Mosquito was not a symbol of technological bravado. It was a demanding machine that required discipline. Canadian crews did not fly the Mosquito because it was easy. They flew it because, when handled correctly, it delivered results. This is where the Canadian contribution fits naturally into the story, not as originators of the concept, but as professionals who proved that the concept could be sustained in production and in combat. The Mosquito rewarded competence and punished complacency. Canadian factories and aircrews learned this quickly, and that learning mattered long after the first sorties. The Mosquito's success makes it tempting to treat its concept as self-evident in hindsight. It was not. The logic behind the aircraft worked only within a narrow band of assumptions. When those assumptions failed, the consequences were immediate. Speed protected the Mosquito only if speed could be maintained. Altitude helped only if it could be managed. Avoidance worked only if interception was delayed. When those conditions broke down, the aircraft had no secondary defense. If caught at low energy, the Mosquito could not absorb punishment. If surprised at low altitude, it could not climb away. If navigation errors extended exposure time, interception became likely. Losses occurred. They were not hidden and they were not trivial. Fire was a constant threat, as it was to all fuel-carrying aircraft of the era. Structural damage that might be survivable in a heavily armored bomber could be catastrophic for a lightly built aircraft operating at high speed. This does not diminish the Mosquito's achievement, it clarifies it. The aircraft succeeded not because it was universally superior, but because it was used with restraint and precision. Crews respected its limits. Planners selected missions where its strengths mattered and avoided situations where its weaknesses dominated. This discipline was the real innovation. The Mosquito did not change air combat by rewriting the laws of physics. It changed air combat by showing that under the right conditions, speed and planning could replace mass and armor for specific tasks. That lesson was not universally applicable. Most aircraft could not operate inside such narrow margins. Most aircrews could not be asked to accept such unforgiving risk. This is why the Mosquito did not replace heavy bombers, and why its philosophy was adopted selectively, not universally. In the end, the Mosquito stands as an example of engineering honesty. It did not promise protection where none existed. It did not rely on redundancy to mask error. It demanded that every assumption be respected, from factory floor to cockpit. When logic said the aircraft should not work, it was partly right. It should not have worked under most conditions. It worked only because those conditions were chosen carefully, enforced relentlessly, and understood completely. For Canadian factories and Canadian crews, this was not a story of legend or bravado. It was a story of execution. Building and flying the Mosquito demanded quiet competence, strict discipline, and an acceptance that there would be no margin for showmanship. There was no room for shortcuts, no tolerance for exaggeration, and no safety net once the aircraft was committed to its mission. That approach, careful planning, respect for limits, and responsibility for outcomes, reflects something deeply recognizable in the Canadian wartime experience. Not loud claims, not heroic myth-making, but doing a difficult job properly, under pressure, and accepting the risks without pretending they did not exist. That is the real story of the Mosquito. Not a miracle, not a myth, but a narrow, disciplined success achieved where logic bent but never broke.